So first thing we will basically see that what are the different applications of CFD, okay, in industry. So see, CFD is basically a general field, okay. When I say general, in the sense, solving equations. This is common, whether irrespective of whatever application you are running, right? So now there are majorly, four applications in CFD. Like there are a lot of, but I'll be talking much more, with respect to the kind of courses we are offering in Skill-Lync and what kind of jobs you can expect out of this after doing such kind of courses. So first is basically IC engine applications. Second is basically aerodynamics application. Third is turbo machineries. Fourth is HVAC. These are applications of CFD, different applications. Now let's say Vivek is a CFD engineer, Mehul is a CFD engineer, okay. Now Vivek is saying that, okay, basically background of CFD remains same. So, let's say in background, what each solver does is it will basically solves set of partial differential equations, correct? Right? And this partial differential equation is nothing but it will solve Navier-Stokes equation. And Navier-Stokes equation is nothing but combination of continuity equation plus momentum equation plus energy equation. Oops. This combination will form your Navier-Stokes equation. Now there are various forms of Navier-Stokes equation. We'll not go into the math of those things, okay. Mathematics, if you want to understand the mathematics, and which is very important, right? So there is a course called Introduction to CFD using MATLAB and OpenFOAM. So in that, these things are covered, like, how Navier-Stokes equation is derived, how to read Navier-Stokes equation, and what are the different terms in the Navier-Stokes equation, right? All these things is taught, but today's session is not basically focusing on understanding the mathematics behind the solvers or how solver solves the equation, okay. So basically today's focus will be there is a graphical user interface with you, for example ANSYS Fluent or Star CCM Plus or Convert CFD. These are the software, okay. Software is the software. When you open that software, you will get to see graphical user interface, where you can basically set up the case, provide the boundary conditions, provide the input values, initial conditions, boundary conditions, and finally you run the case. So these are couple of software, SC Flow, etc., etc. But the thing is, most of the time what people, I have encountered in my career is when I started my career in CFD, right? People used to ask, okay, which software is widely used in the industry? Okay, which software I should learn? See, it is not about which software you should learn, guys. It is very simple. If you're basically, your question should be like, what should I learn? Meaning, like what all things in general you will tell me to learn so that I can get a good job in CFD. That is to be very frank, I will be very upfront here, okay. Everyone, we are doing first thing to upskill ourselves, okay, and we are upskilling ourselves to get a better job. Simple, okay, nothing to shy about. We are doing these things to get a good technical core job, which is everyone's desire, okay. Now to get a job, what you have to do? Obviously, you have to upskill yourself. You have to know the skills. Let's say if you want to get into CFD, you should know the skills of CFD. So for the skills of CFD, what all things I should know? You should know fundamentals of CFD. First thing, fundamentals of CFD. Plus, you should know fluid mechanics. You should know thermodynamics. You should know heat and mass transfer. Correct? Then now, depending upon the application, let's say, okay, I don't like to solve, aerodynamics problem, but I love to solve IC engine problems. Great. CFD remains the same, just the application is changing. If you are interested towards IC engine application and you want to apply the concepts which you learned in the course called Introduction to CFD using MATLAB and OpenFOAM, where you will be learning fundamentals of CFD, which is very important, which everyone should know, irrespective of application engineer or developer. Now, these are the things you are going to learn in this course. Now it's time to now apply what you learn. Now, if you're saying that one person is saying I want to apply those concepts in IC engine application, one is saying I want to apply in aerodynamics application, one is saying I want to apply in turbo, one is saying I am already working in a HVAC industry, I want to apply in HVAC. Great. Take those application area and apply those things. But couple of things which is very important is this, which you should be good at. And if you are not good at, not to worry, you have to basically, if you really want to make your career, it's the right time for you to basically open the standard textbooks, read like a newspaper on a daily basis, right? Start with thermodynamics, then fluid mechanics, then HMT. Don't do in parallel. First, read thermodynamics book by Jonas Angel, if you have heard of, right? Jonas Angel is a very classical book. Then Jonas Angel is having book for all the three, fluid mechanics also, thermodynamics also, heat and mass transfer also. You have to read these three books compulsorily. Whether you know the concept or don't know the concept, if you have not read his book, you have to read the book. Then fundamentals of CFD, right? CFD fundamentals by basically John D. Anderson. Classical book. But this book will be very heavy to understand, and don't directly jump to fundamentals of CFD by John D. Anderson. Disclaimer. Okay. Because it is very heavy to understand, and before you basically read fundamentals of CFD by John D. Anderson, if you're taking a course from Skill-Lync, then you have to first finish this course, because while doing this course, we have made a lot of things we have simplified a lot of things, and you will be basically solving those things, programming it, coding it, and understanding the concepts. And then side by side, there are challenges which will ask you to read certain chapters from this book, which will help you to resolve or solve that challenge. So you have to read those chapters only for now. Once you finish considerable number of courses, like you have done Introduction to CFD, then IC engine course, or aerodynamics course, or any 2-3 courses if you have done, then you are in the good position to start reading this book, heavy books, right? If you are basically IC engine oriented, then you have to read IC engines by John Haywood, right? If you are basically going in aerodynamics, then read aerodynamics by John Haywood, same author. It is also having in turbo machinery also, but there are different good books in turbo and HVAC also, right? Depends. Now, if you're interested in IC engine, don't read aerodynamics book. Out of curiosity, it is fine, but once you get a job, then basically fulfill your curiosities, right? So first focus on what is your area of interest in CFD also, right? You decided that, okay, I want to do in CFD because I love fluid mechanics, thermodynamics, HMT. Great. Now you have to basically learn from some common subjects which is required, so that you basically make your fundamental very strong. Once your fundamentals are strong, then you basically have to decide that whether I want to go in IC engines, aero, turbo, or HVAC, and accordingly basically choose the books, basically choose the courses, and then basically you will be having the right skill set with you, right number of projects, right set of projects, which will be help you in achieving the ultimate goal, that is to get a technical core job. Simple. Now, which software to learn? Okay, if you are too much confused, if you want to start with ANSYS, start with ANSYS. If you want to start with Convert CFD, because there are a lot of courses in Convert CFD, start with Convert CFD. If you want to start with Star C++, start with Star C++. But we were having the course on Star C++, but it's not there now. Okay, we have removed that. But we have in ANSYS Flow and Convert CFD, SC Flow. Start with one software and master it. Because I'll tell you, let's say you started with Convert CFD. Today we are going to work on this. Let's say you started with this. Now suddenly in the industry they are saying that okay, a person who knows ANSYS fluent, openings are there for that guy. Now you will be panic, hey man, I don't know ANSYS fluent, I have only done Converge, how it will be happening and all. Yeah, how much time you need to learn ANSYS? If you very well know Convert CFD, how much time you will be needing in ANSYS fluent? It's similar to, like, MATLAB and Python. Yesterday we discussed, right? If you know how to build a logic and write a code in MATLAB, the logic remains the same. In Python also logic remains the same. You just need to learn the language, the syntax, which will take hardly a week. That's it. Learn it. And opportunities, there are hundreds of opportunities coming every month. Trust me, guys. But you should be having the right skill set. When person, you're saying that I did aerodynamics projects, and if it is asking you the simple question, let me rub this. If it is asking you the simple question that, hey, basically you said you did in aerodynamics, right? This is an airfoil, for example. Okay, I made it very bad, but that's fine. And from here, wind is coming. Okay, free stream velocity. Now it is saying that explain me, okay, why there is a recirculation zone here. Why recirculation zone is forming?
So because of flow separation.
No. I'm not asking you now, but I'm telling you the simple thing that why recirculation zone is happening. Simple question, right? Or it is basically telling you that on what basis you will decide the size of the wind tunnel. What should be the wind tunnel size, right? What should be the inflow length? What should be the outflow length? What should be the height of the wind tunnel, and why? If you're saying something like it should be 5 times the length of the body, 15 times the length of, why? What will happen if I don't keep that much length? Then at that point of time, if you're stuck, there you go. That is what is called fundamental. So whenever you are doing any project and challenges, when you're taking up the course, make sure you're reading research papers. Very important. Let's say there is a first challenge on channel flow, okay? For example, which we are going to do today, flow through channel. So there is a rectangular duct, okay, and flow is coming. This is inlet, this is outlet, flow is coming. Now you have to basically understand. You have to basically read a research paper. Just type in the Google that research paper on flow through a duct, rectangular duct, okay, flow through a circular duct, and see what author has actually done there, what he is trying to explain, what kind of plots he is, what kind of graphs he is plotting, what kind of contours he is showing. In the contours, what he is explaining, that is the thing you have to also do in your report. Your report should be technically detailed, right? Getting the colorful plots and not explaining those contours and plots, the report is of no use, complete waste. Okay, show them that how you set up the case step by step, show them the results, show what is the aim of this project, show what is the introduction, show formula what you are using, show the calculations what you are doing, right? It should be a detailed report, like a black book. You basically created a black book for your BE final year project. You have to basically write your report for each and every challenge. That is a 12 weeks course, means 12 challenges at least. Okay, in this there will be, let's say, 9 challenges plus 3 to 4 projects. For these 9 challenges and 3 to 4 projects, you have to basically write the detailed technical reports and submit it for grading. This is the hard part, and this is where the people fall short. If people are doing this thing, they are reading research paper, because when you're reading research paper, guys, trust me, 75% of the thing you will not understand, or 60% of the thing you will not understand. That's okay. That is where you have to learn those things which you don't understood. Sometimes there will be technical terms you have heard, but you don't know the meaning. Okay, this is a good time to understand that, right? And try to understand it, read from standard textbook what it does mean, what does it mean. Ask your support engineer, because support engineer will never tell you no, will not help you out with these things, right? We also keep fundamental sessions by industry experts, right? So basically, if TAC is telling that, okay, this is the particular thing which I need to take a look at, or I will basically arrange a session for you from the industry expert. Great, that's a good opportunity for you to learn from the industry expert, right? You just have to ask, right? If you're shying, in asking your question that, hey, what he will think. Okay, you are a student now. Okay, you're a student and you're shying. Imagine that by hook or by crook, if you're getting a job somewhere, but that doubt is still there, right? If you have not asked this doubt and you are having a doubt, and if you're not asking, just like it is very, it seems like simple. If it is simple, you should know. If you don't know, it is not simple. Okay, that mentality you should carry. Now, if you have not asked this question, by hook or by crook, if you are getting a good job, let's say in your job the same problem comes. Now if you're asking this question to your manager or your technical specialist, now it is a shameful situation for you. Then also, if you're not asking there also, then this will not leave you. Pakka. So it's better when you're learning, ask. And if you're not understood one time, ask at second time, third time. Till the time you're not understanding, ask. And support engineer will sometimes give you the answer, sometimes he will guide you. That, hey, read this, read that. Then do that. Do your own research also. Because you are aiming to get into R&D department. And if you are basically expecting that we will spoon feed you for every time for all the questions, then how you can expect that you will be getting a job in R&D? You will be able to finish this course with our help. All the courses will see, clarifying all your doubts is a piece of cake for us, because we have done this course multiple times and we are supporting this course from past 3 to 4 years. Or any support engineer who is going to do this, he's going to basically easily resolve your query. But why he's asking you to go and read, he's guiding you and not resolving your query on the fly, because he want to basically make you like him or better than him, because the ultimate goal is to get a job, right? See, out of 100, 98 people will be here to get a job. 2 people will be like, okay, I already have a job, I am upskilling myself. That's fine. Okay, so understand this thing and have that mentality. Okay, and you will be getting the TAC support all the time. No worries at all. Ask. You will be getting industrial expert sessions. Ask. You have to request for it, right? Request it, we will arrange it for you. Give us the set of questions which you want to ask. If you feel that we internal team will be able to help you out with this, well, we will arrange a session on the fly. If we feel that, okay, industry expert is needed for resolving these queries, we'll arrange it for you. That is what Skill-Lync is doing. Okay, so this was the introduction. Okay, but let's move on to the actual thing which we we are going to do. So basically, before we kickstart our session, okay, session is already kickstarted. Okay, but before we actually move on to the setting up the case and all this stuff, I would like to basically share my screen. This is basically a 2D cavitation problem, multi-phase problem. Okay, where air is also there and liquid is also there, and this is basically Winkelhofer nozzle. Okay, which is used basically in the diesel injectors and all. Okay, so if I play this, you can see the animation, right? So if you see that here we are basically seeing that how the mass flow rate is continuously changing in a rapid manner. Okay, and how basically void fraction is changing and how we are able to capture the physics here, right? So again, I'll play it. You can just take a look. Okay, so now the thing is, this is a multi-phase problem, 2D cavitation, which is application of, again, IC engines, HVAC. Okay, second is centrifugal pump. Okay, this is a part of a turbo machinery, right? So if I play this, right, so here you have to understand that, okay, this colorful animation you've got, great, but you have to explain what is going on. You should be able to explain that, okay, at the tip of the turbine blade, why there is a maximum velocity, right? Why there is a diverging section at the outlet, right? What is the importance of volute, right? Then finally, you have to basically run the performance study, right? So these are the things you should be able to explain. See, getting the colorful plots is not a big deal, right? But you should be able to explain this, physics which is happening, and that then only you will be called as an application engineer, because You have to see whether this software is able to capture the physics or not, if it is set up correctly. Second is, this is basically a single cabinet, okay, of hot oil, cold oil of a data center. So basically this is a data center, okay, but we have only one cabinet we have put for initial setup, but there is a multiple cabinet simulation also, which I'll show you. But take a look, right? So in the inside this cabinet, basically there is a heat source, okay. In the server room there are chips and all, which is creating a lot of heat. So there is a heat source which is generating a lot of heat, and there is a plenum region below, from where the cool air is basically provided through the holes to the server room. Now cold air basically is coming into the server room from the plenum, and it is basically picking up the heat from the server room, and it is basically throwing that extra heat out into the atmosphere. Now if you closely look that, why outlet is basically at the top, right? We have provided the outlet at the top, and you can see that the vectors are moving upwards. So why? Because when the cool air is coming and when it is getting sucked into the cabinet, it is picking up the heat, and when the temperature increases of the air, its density decreases. Correct? When the density decreases, it is bound to move upwards. So that's why outlet is up. So these are the things you should explain, right? Anything in engineering is not for the showpiece or just to show that it looks good. No. So you should be able to explain, right? This is again the same thing, but from the different view. Right? So see, it is picking up the heat, the hot air being more buoyant. It is basically taking the hot air and basically vented out into the atmosphere. This is what turbocharger. Okay, again the application of IC engines, turbo machineries, HVAC, correct? So this is a turbocharger. Now basically a hot gas is coming, and that hot gas is having high enthalpy, okay, and high enthalpy is basically hitting the turbine blade, and it is making the turbine rotate. So if you see, slowly after hitting for some time, it has slowly started rotating. The wheel has slowly started rotating. So now if you can see, there is a pressure plot. So at the turbine blade where it is hitting, there is a stagnation zone. There is bound to happen the high pressure. Right? So these are the things you should be able to explain. And these are the actual projects you will be getting when you're basically taking up the courses on turbo machineries, HVAC, and IC engines and all. Right? So this is specifically in turbo and HVAC. Okay. This is aerodynamics problem. This is a FSA racing car, right? So basically, if I play it, so this is basically showing the velocity contour, right? You have to explain why there is a separation zone, right? Here basically the terminologies like boundary layer separation and all these things will come, correct, which we are going to discuss. Right? This is Ahmad body. Okay, Ahmad body is basically structure model which is basically benchmarked. So whatever the results we get, we basically compare against the Ahmad body results to basically see how much it is results are deviated from Ahmad body results, right? So again you can see it's a velocity contour, and there is a again the separation zone, right? And because of this separation zone, there is creating a low pressure region at the back end, and there is a high pressure at the front, and this high pressure and low pressure is creating a drag force which is responsible for drag, right? This is basically IC engine application. This is basically a diesel engine, okay, with different ball shape. This is open W and omega, right? So we have actually ran the sector of it, okay, not the complete 360-degree engine, to save the computational time, right? So we are basically comparing heroic suit and NOx, right? So here engine is getting compressing the air fuel mixture. Sorry, it is compressing the air and then fuel is getting injected. It's a diesel engine, right? So now if you can see, in heroic suit, in one engine heroic suit is less, in another engine NOx is more. correct? And so why it is happening, you have to explain that, right? So this is port fuel injected engine, right? So in the port, basically in intake port, fuel is getting injected and it is getting mixed with the air, and mixture is basically entering into the cylinder region, and this is what it is, right? So if you see, basically fuel air mixture came, intake stroke, right? There you go. Correct. This is basically Ahmed body again, right? We have basically streamlined this so to understand the results, how it is, streamlined, and then how there is a turbulent region. This is airfoil, right? So for different angle of attacks, we are studying, right? So for angle of attack of 15, it has shown a lot of vortices being formed. Right? This is FSA racing car. Right? This is proportional valve. Okay, so proportional valve is widely used in the industry in space and space industry and all, right? Because there should be no leakages, and valves are used in various applications, right? So this is one of the called proportional valve. So here it is a fluid structure interaction. So here you are dealing with solid and fluid. So basically fluid is creating a pressure and it is making this, valve, lift up. Okay, because it will require certain, newtons of force to basically, push this valve up, because there is already a, spring, which is making this valve, sit on this seat. So basically this is what is shown here. So this is again a part of HVAC and turbo machineries. Right? Then this is what I was talking about, multiple cabinets. Okay, this is hotel coldwell multiple cabinets. So if I play, again capturing the same, if you can see, there is a, in within the cabinets there is a red, dark red, and then cold air from the bottom region is coming, and it is basically picking up the heat. And if you can see that through the outlets, hot air is being vented out. Correct. I'll again play it. See, from the cabinet, high temperature is getting generated. From plenum, cold air came, green in color, picking up the heat and vented out into the atmosphere from outlet at the top. This is basically my project. Okay, I did this. Okay, this is not the part of the course, but this is basically, the compressor wheel. Okay, and the diffuser section. So we basically, I'm trying to basically, do the project on the complete, engine. Okay, in which basically there is a compressor wheel, diffuser section, combustion chamber, nozzle, right? So this is one part of it. So we can do these things. If you, we can basically try out multiple things, and you can basically, implement those things. Basically, if I know how to set up turbo machinery's case, this is also turbo machinery, right? If I know that how to do that, I will also know how to do this, right? So basically this is what are the projects which you are actually going to work on, right? Provided you have to understand that what is my area of interest. All right, now basically let me open, this thing. Okay, this is convert CFD software. Okay, this is what we tell. This is a software, and this is what you're looking at is the graphical user interface, with the help of which you will be able to create, the geometry if you want, or if geometry is already there, you can basically import the geometries. Okay, and you can set up the case. For example, let's take a very simple example. Okay, I will not be able to explain the tough, challenges or projects like shell and tube heat exchanger, right? This is one of the project, shell and tube heat exchanger, right? So this is the geometry we will not create in, Converge. This will be created in the CAD. Okay, CATIA or NXCAD or something, but we will provide you, because whole idea of a CFD engineer is not to design, but take the design from the design engineer, and your job is to basically clean up the geometry, create the volumetric mesh, set up the case. That's it, right? So if you basically see, take a look at this geometry and all, right? If you closely look, so if I just create triangles. So this is, yeah, yesterday I told you, if you were there, that we have created one project in MATLAB to create a STL file and create a holes. I mentioned that if if you know that statement. So these are called as the scale files. Okay. So if you see entire geometry, the surface is, distributed into n number of triangles. So I'll select triangles here. I'll basically select basic. Okay. I'll select by surface. I'll just hide this. Okay. If you can see, this is the inner baffles and everything, and inner tubes, shell and tube exchanger. Right. So this is what you have to set up this case. It looks simple, right? But when it comes to cleaning up the geometry, removing the unnecessary parts, right, which is not necessary to basically do this simulation, or it doesn't have any involvement in what results you are looking at. So that is what you have to learn. And this methodology, if you learn, irrespective of what domain it is, you are good to go. Few things will be obviously little bit changed, the way it is programmed at the back end. But if I tell you that if you have to set up the case, there is a CFL number, there is input conditions, those things will not change. Mesh, those things will not change. Correct. So that is what. So basically, to do this project alone, to clean up the geometry and setting up this case, it took around 1.5 weeks. Okay. And then basically we basically simplified the geometry a bit, because it will be anyways very difficult for students. So but we want to, but I didn't uh, simplified a lot. I want students to struggle here and ask us the question, so that when they are making a mistake, it will be helpful to them only. Okay. So this is what shell and tube heat exchanger. I'll close this because that is what I want to show you here. Okay. Close this tab. Great. Okay. Now the thing is, I will open the new file here. Okay. Now what we'll do is I told you, like, flow through the duct, rectangular duct, right? So what I'll do is I'll basically go to create shapes. I'll select the rectangle. Okay. And I'll basically quickly draw a shape here. Okay. Or I'll provide basically a side, let's say 0.1, 0.1. Okay. And basically I will create a plane here. Okay. Side A, side B. Now what I can do is I can copy the edges, select by open edge. Don't hang. Okay. Oh, great. Okay. What I'll do is I'll just patch it. Okay. There are n number of ways how to do this. Okay. This is one of the way I'm showing you. So I'll patch this. I'll pick up this. Okay. All right. And apply. I'll patch this also. Okay. Now what I'll do is basically I will loft it. Okay, loft the edges. Okay, so if you can see, what I did is I loft the edges. Okay, I created a open loop, and then there is an option called to loft the edge. And now, but you can see there is an open edge here. Okay, so what I'll do is I'll now patch it. Okay, which I did earlier. Okay, so here patch it through basically open edge. Okay, I have to select here open edge. Okay, option is there, and edge option you have to select. And if I select this, it will select the open edge, apply, and basically I'll just rotate a geometry a bit. Again, I'll select the open edge and I'll just patch it. Done. So now this my duct is ready. Okay, this is my duct, simple geometry. Now what I have to do, I have to basically set up the case. How I will set up the case? Okay, I so to set up the case, I want to understand. I'm basically trying to understand the problem flow through channel. So if a fluid is coming from one inlet, from the side which is inlet, then how it is behaving. So what I'll do is I'll just go to case setup, or before case setup, what I have to do in Converge is I have to basically, so create a flag the boundaries, means so that I can provide the boundary conditions, because software should know, right, what is inlet, what is outlet, right, what are side boundaries. So for that I have to basically uh, flag the boundaries so that Converge can understand that okay, this is inlet and this is outlet. So how I'll do is I'll basically go to boundaries. Okay, let's wait. I'll go to basically boundaries. Here you can see, assign triangles to a specified boundary, correct? So here basically I will add, I need how many boundaries? Basically, I need to create multiple boundaries, and let's say I will create 5 boundaries. Okay, starting from 1. So here, if you can see, there 5 boundaries is created. Now what I'll do, this font, I will click on this first boundary. I'll select this triangles. I'll create by any now. Okay, so let me select this triangle and this triangle and the first boundary, and I'll apply. So now this is yellow. Okay, and what I'll tell is this is basically okay. This is basically
Can you
my inlet.
please name the software you are using?
Convert CFD. Convert
Okay.
CFD. This is called as Convert Studio, and since we are doing CFD in Convert, so it is Convert CFD, but you can say Convert Studio or Convert CFD, whatever it is. Okay, so this is inlet, and basically this is, I'll put the other end is outlet. Okay, obviously, right? So I'll put this as outlet. Apply. Now this is outlet. I'll rename it so that for my understanding that what is inlet and what is outlet. Right now, what I'll do, my geometry lost, right? So what I'll do, I'll click on one of the standard view, it will come. Now this I want to run it in a let's say this is top wall, right? Top, and this is bottom. So what I'll do is I will put top and bottom as one boundary. Okay. Why I did? Basically, because those walls are, are going to have the same properties. That is why I did. Okay. Now let's say this is my front. Okay, not this. This is back. Okay. So yes. Front, and I can also put front and back, as a different boundary, not an issue. And as a same boundary or a separate boundary, it doesn't matter. So this is back. Okay. So now this is called as boundary flagging. I have basically flagged the triangles with some color for my understanding and for Converge understanding. Okay. Now what I will do is I have to set up the case, right? So now basically I'll go in case setup. I'll begin the case setup. Okay, from here. Now I want time based because I'm not running the IC engine simulation, which is crank angle based. I'm not running basically turbo machinery, which is crank angle based but non-engine. I'm running the simple channel flow problem, right? So time based. What material? I want to use air by default. So I will click air. If there is any other you can use that also, right? I don't know. I don't want reaction mechanism because no reaction is happening, right? If it is IC engines or something like that where chemical reactions are happening, I'll be needing reaction mechanism file. So here there is no requirement of that, right? And there you go. Then basically simulation parameter. Yeah, I don't want body forces and multiple. No, body forces will be required when you're doing fluid structure interaction, right? Where the factor of gravity will come. Boundary conditions, yes, boundary I need no wall value initialization, no motion setup. Okay. Initial conditions, yes, I want. Okay. Sorry guys for it is being little bit lagging on the computer because multiple tabs are open, right? So bear with me on this.
Sir,
Yeah, go ahead.
in the materials, what are the materials available, or can we like load some other materials? Like
Yeah, absolutely. You can. Let's say if you are using liquid, if you are basically, because in port fuel injected engine, along with air, there is a fuel also, right? Isooctane or N-heptane or whatever, right?
Yes,
So absolutely, you can, and Converge basically provides that, right? So if you basically go in materials, so here if you are saying that liquid simulation is there or solid simulation is there, then it will ask you the material for it.
okay, sir.
Right?
Is there
So,
any limitations to the material, sir?
sorry?
Is there any limitations to the material?
No, if you have the material properties with, so there are inbuilt materials already there, okay, which Converge provides, right? Like aluminum, solid, copper, if you're doing, solid simulation. If you're doing liquid simulation, then there are already, methanol, ethanol, ethyl alcohol, there are n number of properties given, which are inbuilt. You can choose. And let's say if you're using something different, which is not available in Converge library, then you can basically have to create your own Excel file, and then you can import that.
Okay, sir. Thank you.
Okay.
Okay, sir. Thank you.
Great. So initial conditions, absolutely we need initial conditions, right? Because yesterday also we solved the OD45, which was a numerical solver, and here every solver is solving the problem numerically. Okay, so that's why you will never get the exact results. You will be marching towards the accurate results, but you will never get the result which is there is zero error. No, because we are solving numerical and there has to be numerical error. Okay, so all the solvers which are solving are partial differential equations at the back end, right? They need initial conditions because they are going to solve this numerically, and for numerical to solve anything numerically, you need initial conditions. Definitely you need initial conditions. Physical models. Now here there is no spray modeling, no combustion modeling, no emissions. Turbulence also we are not doing here, but if you want you can, but none other models, right? Then basically comes to grid control. Yes, brace grid I want. I will also use fixed embedding. I will tell you what is the meaning of it, right? Then process output, great. Advanced very nothing. Okay, I will apply and yes and done. Okay, confirm. Okay, so now here you have to now provide all the, you have to set up the case. Simple. Here global transport properties, Prandtl number and Schmidt number. Okay, you have to set it up. Now you are setting up. Now if you want to understand what is Prandtl number, what is Schmidt number, what is the importance of it, then you have to basically move towards the mathematical part of the CFD, right? So that's why the fundamental of CFD should be clear, so that when you come across these parameters, you actually know what you are providing and why you are providing, right? In run parameters, let's run a steady state. I want to run steady state. Okay, I'll provide this, right? Then simulation time parameter. Here it will ask for start time, end time, initial time step. We talked about time step yesterday, but not in depth. But this is what is covered in introduction to CFD using MATLAB and OpenFOAM. What is time step? What is the importance of it, right? So usually initial time step is 1 e power minus 9. Why, right? Those questions should come for you, right? For that you have to understand the fundamentals of CFD. Maximum time step we usually keep 1. Why? Again, fundamentals, right? I am not telling you now because otherwise it will be session will go for 5 hours, right? End time basically in cycles. Why? See, when you're setting up, there are times are in three forms. One is in cycles when you're running a steady state. One is in seconds when you're running a transient case. Third one is in crank angle based when you're running IC engines or turbo machineries where there is a rotating fluid is rotating, or some component is rotating. Okay, so let's say cycle I want to keep 15,000 for example. Okay, right? So I will not type much now, but here let's say I'm okay, it will create a problem only. Okay, 15,000 cycle, and here initial time step again 1 e power minus 9 and all you have to put it. Okay, and if I just click on OK now, it will be showing the cross mark because I have not provided the there are some blank spaces. Solver parameters, you have to basically keep this as it is. Okay, now here you can see, right, Navier-Stokes solver type. So at the back end, what it is solving? It is solving the Navier-Stokes equation here, right? Continuity, momentum, right? So density based or pressure based? Always go with density based, right? There is a reason for it. It's a short reason I'll give you, because see, if your Mach number, okay, here there is nothing like supersonic, subsonic flows and all, but if it is a Mach number, basically if your flow is going supersonic, okay, then you have to basically use density based solvers to basically solve, because at the supersonic stage your temperature starts changing, so there you also have to solve the energy equation as well, right? But when you are using pressure based, it doesn't have energy equation. Okay, so you might end up getting a wrong results, right? So to be on the safer side, if it is not a supersonic flow and it doesn't require to solve the energy equation, it will not solve. That's it, right? Then in boundary conditions, this is very important. Now there are two kinds of boundary conditions. Okay, very what we say famous, okay, in CFD for inlet and outlets. Okay, so basically, okay, so here if I go inlet, right, so here it will ask what type of boundary you want. Inlet, so I want inflow, right, so it will be inflow. Now it will ask a lot of things, okay? Whether you want total pressure condition at the inlet, or you want velocity to be mentioned, or you want, temperature boundary condition, depending upon the application. Okay, here I will basically say that, okay, I will provide the total pressure boundary condition here. Okay, let's say 110,325 pascals. Okay, this is what my total inlet pressure is, total pressure. Okay, now here it will ask for the region. We have to create the region and initialization. Now for outlet it will be outflow, correct? For outflow, and now at the outflow it will ask like pressure boundary conditions. So here basically it will not be a total pressure. See, you can't provide total pressure at the inlet also and total pressure at the outlet also. Okay, it can be a condition like inlet total pressure, outlet static pressure. Or if inlet is a velocity boundary condition, then outlet can't be velocity, then outlet has to be static pressure. Now why I can't keep both the, if I can keep both the inlet and outlet as pressure boundary condition, one at total and one is basically static, why I can't provide velocity? So what velocity will provide, right? If there is a velocity at inlet and velocity at outlet, what will drive the flow? There should be something which will drive the flow, right? Because of pressure difference, fluid flows, correct? So that is why we will be having basically these kind of boundary conditions which are very much famous. All right. Now basically in top and bottom, basically you will provide that top and bottom. Basically I want basically what we say, symmetry 2D G-suit interface. I'll say symmetry boundary conditions. Okay, or I can also provide wall boundary condition. Okay, it's a wall, I want to provide it as a wall. Okay, now what is that wall? It is a stationary, it's not moving, so stationary, it is fixed. Okay, now I will keep no slip here. Why I should keep no slip? Anyone can answer this question, like why I should keep no slip and not slip condition here?
Sir, because velocity at the wall will be 0. So
awesome. Okay, so to capture that physics you have to keep it no slip, right?
yes, sir.
If you keep slip, what will happen?
Sir, velocity will not be 0, sir, at the wall.
Correct.
And
what will be the velocity?
Sir, it will be it will be greater than 0, sir.
To be more specific, it will be equal to free stream velocity only.
Yes, sir.
Correct. So
yes, sir.
This is what very important to understand. Okay, I'll share my whiteboard now to explain this concept. Okay, let me share my whiteboard. Let's do some math now.
Yeah, okay. There's a formula as per.
So the stress is 0, right?
Yes, sir. Yes, sir.
The
The stress is 0,
right?
Yeah, but it's also into du by dy, right? Where dy is the vertical distance.
This is a rectangular duct. Okay.
Yeah.
Can you mute yourself? Great. This is a rectangular duct, guys. Okay. This is for all. Now, basically from here, your fluid is coming. So this is the free stream velocity. Okay. Let's say free stream velocity is basically, let's say 5 meters per second. Now understand that this is a wall. So if something is basically touching this wall, it will offer the resistance to it, correct? So basically it is stick. So that the layer of that particular fluid is actually on the wall, and it is at rest only. It is 0, which is affecting other layer of the fluid. And that is why I don't know if you are aware of this or not, but you are getting a parabolic profile, correct? So basically here it will be 0, then it is slowly increasing, right? And at the center it will be maximum, and again then it is slowly decreasing as it is moving towards the. So near the wall we provide no slip, which will basically make sure that near the wall velocity is 0. Okay, so that we will be able to capture this physics, and this to basically capture this physics, we have to provide this as a no slip condition. Okay, and basically the thing which you were talking about of the shear stress, that's a different thing. Here what we are interested to know is dou u by dou y. So let's say this is your y and this is your x. So we are not interested in du by dx, which is very small, but dou u by dou y is what we are interested in. Okay, because at the center there is no resistance, but as we move towards the wall, the first layer which is resisted by the wall of the duct will resist, and the next layer will resist, but this effect will reduce, and at the center there will be maximum velocity, which is u infinity. But if we keep slip condition, right, then everywhere there will be u infinity, and what will happen is everywhere it will be of vector will be of same length. Okay, now for this, what I want to show you guys is, this is a very simple problem, but how you guys have to learn the things. Okay, for that I will show you one of my report. Okay, this is actually the report when I actually started learning CFD and I started with the courses and all, right? So this is how you have to basically do anything you are doing in life, whichever course, whichever thing you are doing for the first time and all. This is how you should open your Word doc, and you have to basically start making notes, start making the things which you don't know. Okay, so this is basically the contour. This is called as a contour for velocity after running 7,000 cycles. If you can see at the center, the velocity is maximum, right? And near the wall, the velocity is almost zero, right? So physics is captured. Now this is what I was talking about. Focus on this particular diagram. So this is the mesh. Okay, so now if you closely look, I have refined the mesh near the walls, and I have kept the mesh a bit big at the center, right? So this is called as mesh optimization. See, I don't want to keep lot of, I don't want to increase my mesh count, to a very high number, because that will directly impact our computational time. More the number of mesh elements, that many times solver has to solve the equation. Understand that. If there are 5 blocks which are seen here, the Navier-Stokes equation will be solved 5 times. If there are 100 blocks, for 100 times Navier-Stokes equation will be solved. If there are 2000 blocks, for 2000 blocks it has to solve. So it is affecting your computational time, and also it will directly impact your memory, because more the number of cells, more will be the calculation. It will require more space, more RAM. Okay, so we have to basically optimize the things, and that is what a true CFD engineer is there. So it is not wasting computational time and energy, and requiring a lot of space unnecessarily. He has to basically see that where I need finer mesh, where I need coarser mesh. See, anyways, at the center, however big the mesh element is, it is going to be u infinity only, free stream velocity. But we want to capture the physics near the walls, because that is where velocity is zero, and we want to basically see that it is giving us the parabolic profile, Hagen-Poiseuille flow, right? So that is what, this is the mesh after 6,000 cycle. This was the mesh at the zero iterations, right? So if you see, the mesh is getting refined and refined, right? So that is what basically, that is this thing, specifically I need here at the near the top and the bottom wall, I need my mesh to to get refined. Let's say I want such 2 layers or 3 layers. So you can see there are 2 layers of refined mesh. So if I open my Converge Studio, and if I close this, I'll open the fixed embedding, this thing, and here it will ask like for which boundary you want. So I have not defined yet the boundary top and bottom. So here I will select that. So let me do that. Then only it will make sense to do this. So in the boundary, let me basically create top and bottom, and top and bottom is just no slip. Okay, front is basically, I will keep it, I can keep it as a wall also, and I will keep as symmetry. Okay, it will ask for the region also. I'll create region for it. Okay, so let's say I want to create embedding. Okay, which I want to basically refine my mesh, near the top and bottom. So I will basically create, okay, top and bottom is one only, that's good. So here it is asking, right, entity, you want to basically, I want to go with the boundary. Okay, so now sequential, no, I want permanent, so it will be permanently refined there. Scale, so let's say my base mesh is 2 mm and I want their 0.5 mm. So here the calculation will be that whatever is your base grade divided by 2 power n. Okay, so basically if my base mesh is 4 mm and I want 2 mm this thing, so 4 by basically 2 is 2, correct? So scale should be 1 here. And how many layers I want? Such 2 mm layers, how many I want? 1? No, I want 3. So that there will be 3 layers near the top and bottom. And when I hit OK, so basically which boundary? So here, which boundary ID, right? So I want for top and bottom. So, and I will click OK. And now for top and bottom, this kind of thing you will be able to see. Okay. This kind of thing you'll be able to see, right? Near the top and bottom, the mesh is refined and it is having 2 layers, because while setting up this case, I said, no, I think 3 layers are there. Okay. So this is how I am capturing all the results for my reference. Then basically I'm plotting the velocity plots. Then in Paraview, which is the post-processing tool, I'm basically creating a probe. If you can see a vertical line at the extreme left of the channel, I'm basically trying to plot velocities, right? Then I have some doubts. When I was learning this, so I was having doubts. So I will make a note of it. Why it is showing graph till only 0.01 second. Then I have another why, and what does x-axis represent, right? Is there any option here to label the axis automatically? So whatever the questions I was having, I kept on mentioning here. And whenever there is a support session, I will ask my support engineer, and they will explain me, and I will basically write it here. And I will document everything, so that in future, if I basically come here, I just have to read once and it's done. That's it. I will never forget these things. So this is how the approach should be for you guys to do any kind of course, and that is the reason I'm showing you that this kind of report you should have, rough reports for each and every challenge, right? See, this is y and z component at here. Then this is again the velocity at along y and z, right? Then this is the x component of velocity along this. So this is a parabolic profile I got, correct? This is what I want to see, right? From top to bottom, the probe is there, and I'm basically interested in knowing the x component of velocity along y axis. Confused? Are you confused with this statement?
A little bit, sir. Can you go?
Little bit, great. So I would love to explain this. Let me clear this. Let me know you are able to see my whiteboard, right?
Yes,
Yes,
sir.
sir.
Yes, sir.
What I meant by x component of velocity along y-axis. So basically, this is a rectangular duct. Okay, and what I did is, this volume I basically meshed it. I meshed it. Now, basically, as we said that dou u by dou y is very significant, right? Because near the wall, so this is y and this is x. So if you go along y, here it is 0 velocity, here it is 0 velocity, in between it is maximum 5 meters per second if free stream velocity is that much. So it is changing a lot, right? the gradient is along the y-axis, correct?
Yes, sir.
So I want to basically see at any random location that, okay, here I want to see how the velocity is changing at this probe. So I will create a probe in ParaView or the Insight, which is a post-processing tool. And what I will do is, I'll basically, I want to see which component of, I am interested in X component, right? X, because velocity is having X, Y, Z components. So I'm interested in this component, right? Which is nothing but X component of velocity. Here it is 0, here it is 0, here it is X component. And basically I am getting this parabolic profile. This is X component of velocity. So what I'm doing is, I have created a probe, and then what I'm plotting is in ParaView that I basically on x-axis I'm basically having y distance, meaning from here to here the distance is there. So this is 0 from distance point of view, and this is, let's say, this is 5 meters, which is very large, but it's okay. So this is basically 5 meters. From 0 to 5 meters, from 0 meter to 5 meters, I want to see how velocity is changing. So here the velocity is, and on y-axis I am having velocity, x component of velocity. So x component velocity at 0 is 0. I'll start here. X component of velocity at 5 meters is 0. It will end here. And in between somewhere, it is maximum, which is 5 meters per second, which is this. Now this is x component of velocity graph along y-axis. Is it clear? Guys?
Yes, sir. Yes.
Yes, sir.
Great. So now, how many mesh points should be there to capture this? See, if I say that we should not have a lot of mesh count, otherwise that will increase. So if I only have like this, do you think we will be able to capture the physics?
So no, sir.
No.
Right?
No.
Because there are only 3 points you'll be getting, one here, one here, one here, which will be a triangle. Only 3 data points you have. So basically, to capture any physics, make sure that you are having at least 10 cells. Okay, and now you have to basically do some smart thing also. What is the smart thing you have to do? What is your area of interest? You want to understand how x component of velocity is changing along y-axis, correct? So you need 6 to 10 cells along y, okay, along this direction you want, right? So you can basically have like this, something like this, 6 to 10 cells, like layers like this. But along x, we are not interested to know. So instead of having, this kind of mesh where ultimately your mesh count is increasing a lot, what you can do is you can have the mesh basically like the stretched mesh, right? Like this, having more number of layers along y, but having less number of partitions along x. Because you are not interested in knowing the physics along x, because along x the du by dx is much less than dou u by dou y. So you want to capture this physics and not this. So why to have a lot of cells along x, have a lot of cells along y, and that is what Converge software provides, and any software provides. How many cells you want in x direction, how many cells you want in y direction, and how many in z. If it is important to have cells in all the directions, have it. If it is not important, then why to increase the computational time and why to waste energy? Okay, so this is another important thing which you have to keep in mind.
As you told now that velocity profile, this one, sir, x x along y distance, sir. But where did you check it? Means in the fully developed region, or
exactly? You can check at any at any location. So I have basically created at the middle of the center. I have here created at the extreme left, and in the below figures I have also created at the extreme right, correct? So here, if you see extreme right, I'm getting a very, good parabola, correct? Compared to in the middle, this one. So now this is where your flow will develop completely. And there are chances your flow might not get developed also. So that is where, if you're interested, basically, if you want your flow to get completely developed, you have to basically check this out, and then you have to play with the boundary conditions, length of the pipe, and all these things. That is what, depends upon what kind of things you are looking at, right? Then again, one doubt came to me, so I basically make a note of it. So the reason I'm showing these things to you is to basically to tell you and convey you the message that this is how the course needs to be learned, right? You should document each and everything, whatever is the doubt. So how velocity can be negative? Yeah, I was having this kind of doubts. Can you imagine? Okay, so I didn't basically shy that, okay, how can I ask this? I have doubt, I asked, it is clear, I made a note of it, answer of it. So this is, I have basically, make a lot of notes about whatever I understood after the support session, while watching the video, while writing the reports and all. So if I want to show you my folder, right? So let me show you my folder here. Okay. So D drive. So this is converged runs, my folder. And you can see these are all the things I have done so far. Okay, for every project there is a report and all, and then there is another folder called all notes for simulations Mehul. So if I open this, you will see these are all the notes I have created for myself. Why fuel injectors? What is volumetric efficiency? What is viscosity ratio? Right? What is turbulent versus molecular viscosity? What is steady state versus transient state? Okay, some important things in converge. Right? Shock waves concept. Right? Segmentation fault. There will be a lot of errors you will be encountering while running the case. What is that? Right? PFI diesel FAQs. Right? Points to be included in PPT. Prandtl-Meyer shock flow problem. Right? Memory usage. Parallel block size too small. Law of the wall concepts. Right? Then IC engine simulation crashes. What are the errors and how I resolved it, right? Hot oil, cold oil. For each and everything, if you see, even for isosurface and all, I'm not very good with design. So when I was creating some of the design in SolidWorks and CATIA, I basically make a note of it, that how I did, right? Distance error, conjugate heat transfer simulations. You will get all these simulation, conjugate heat transfer, multiphase problem, internal flows, external flows, combustion, reactive flows, everything you are going to do this. Correct? So this is how you have to basically, make notes, because whenever it is needed, you can open it, just take a look, and you will just within, for 10-15 minutes, everything will be getting revised for you. Okay. Now, okay. Okay, so this is the reason I showed you this thing. Take a look. Okay. Then basically, let me take you to converge. Okay, so I think I can close this file now. Now this is basically airfoil problem. Okay, now you'll say, okay, how it is, right? So let me basically hide a few embeddings and all this stuff. Okay, so that it is visible. So can you see it is a airfoil shape, and this is basically a wind tunnel, and I'm running this as a 2D. So along Z, it doesn't matter how much long or short the wind tunnel is, because it is anyways 2D. Okay, so it doesn't matter. So I have created a very short, so to save the time, simple, right? And I have created a setup. Okay, if you can see, this is the airfoil. I basically set up the case here, if you can see on the right hand side. Okay, then we have to diagnose here. Okay, so if I basically find here, you will see these are the kind of errors which we have to resolve. If there are any intersection errors. if there are any non-manifold problems, open edges, overlapping triangles, normal orientation, right? So if I enable the normals, your normal should be pointing towards the domain, right? So if this is the case, you will get very wrong results. Okay. So if I will just transform my normals. Okay. I'll just create the entire surface. I'll normal, change. I'll select the triangle, apply. Right. So if I basically remove this, great. So if I basically hide this, you can basically see it is not done. Again, I have to do this and apply. Okay. Now all the normals are pointing inside the domain. So normal orientation will basically tell you that tell the solver that, hey, which side is the fluid and where you have to solve. If it is pointing outside, there is no mesh at all outside. Okay. If there is no mesh, how solver will be solving? Because solver will be solving in the mesh elements only, right? So this is what you have to basically keep in mind. So these are the things which you will be able to understand while doing the course in depth. Okay. But the thing is, the whole point of telling you those things is basically this is how you will be setting up the case. Okay. In Converge, you will be flagging the boundaries, you will set up the case, clean up the geometries and all. And here is basically the airfoil geometry, PPT, okay, which I created. And basically these are the things that we have to do, right? What is the steps you followed? What kind of formulas you used? Rho VL by mu, right? First I ran the steady state simulation, okay, for 25,000 cycle, 10,000 cycle, 15,000 cycle and all. And finally I basically, got this kind of results, right? This is not the good results. Why? See, initially till 15,000 cycles, solution was converged. But after 15,000 cycles, something happened and solution blown up, right? So this is not good, right? Solution should not blow up. It should come to the steady state like a straight line. Okay. So this is where, when the steady state, simulation is not giving you the converged result, you have to, move on to transient results, transient simulation. Then basically these are the plots which I plotted: angle of attack versus drag coefficient. Basically, I made the calculation of, I took the drag force formula, put the values which I basically received after running the simulation, and calculated and plotted this using Excel, right? So as the angle of attack is increasing, my drag force is also increasing because drag coefficient is increasing. Lift coefficient, my lift is increasing, then decreasing, then increasing. This is the trend I'm getting from the steady state solution, which I should not. The trend is right, but the solution is blown up, so I can't trust on these results, right? So I have to run the steady state. This is basically the steady state simulation results. I'll just show you if it is allowing me to play. Okay, never mind, I'll open it from there, right? So this is the conclusion and future. In steady state scenario, we observe that the values of drag force and lift force, which is pressure along X and Y, are fluctuating a lot and not getting a converged result. So how can you trust it, right? Hence, there is need to perform the transient simulation. So steady state will be done very quickly. Transient state will basically take a lot of time because it will solve all the equation very accurately, and it will basically, try to basically come to the convergence after running every iteration. But steady state will not do that. Steady state will be like end result. It will focus on the end result. It will try to go to till the end result anyhow. So that's why steady state sometimes give you the results, sometimes it won't give you. So that's why when it is not giving you the converged results, you have to go for the transient state simulation. And this is what I set up for the transient state. This is the results I'm getting. See how nicely it is converged, right? Lift force, the drag force, right? Then this is the averaging window I'm taking, that the last 0.5 seconds I've taken for basically making those plots. Okay. Then basically this is how it is looking, right? Pressure along X for angle for 1 degree angle of attack, for 5 degree angle of attack, for 10 degree angle of attack, and 15 degree. So when the airfoil's angle of attack is changing, we are saying that how it is impacting the drag force and the lift force. That is the ultimate study we want to do, right? So basically, this is what the calculation I did. Angle of attack versus pressure force average over last 0.5 seconds. Then I calculated the drag force. Right? We all know the drag force coefficient formula. Calculated, used Excel, plotted the graph for 1 degree, 5 degree, 10 degree, and 15 degrees. So as the angle of attack is increasing, drag force is increasing. Very valid results. This is the averaging window for lift force. Now it is increasing. 10 degree till 10 degree, it is increasing. If you are increasing the lift more, or angle of attack, if you are increasing, lift is decreasing. Now that is what the stalling is. So you have to basically talk about stalling in your report and all, right? Because that is what we are focusing on. Okay, till what angle of attack my drag force is increasing continuously, but after 10 degree my lift force started to reduce. So what's the benefit of burning a lot of fuel, right? So that is what in industry people are looking for. This is the animation. I think here also it will not run. Okay, I will open it separately for you guys. This is Y plus. So obviously in aerodynamic studies, you have to basically understand what is Y plus, because that will basically decide, what should be the turbulence model you should use. Okay. Basically it will decide that, how many cells you will be needing, right? And depending upon the application, you have to basically decide. So this is a kind of a very heavy topic. We'll not talk much about Y plus, but yes, in the course, you will get to learn a lot about Y plus, and in fact, you are going to implement it. You are going to use Y plus calculator and everything to basically, for this input conditions, what should be my Y plus, and depending upon you will be doing the reverse calculation to see you are not overshooting on cell count. So your Y plus, if your Y plus is very low, you will be, see, Y plus 1 means you are capturing the laminar boundary conditions also. Okay. So, and if your Y plus is between 30 and 100, you are basically in the log low region or turbulence region, right? So to capture, the laminar region also, you need a very powerful computers, 120 GB RAM and something like that, or even more. Okay. We are having around 116 GB RAM PC. For that also, we didn't, went for Y plus 1. We were able to go till Y plus 30. Okay, then that is also good thing, because that is also going to give you reasonable results. Okay, and these are the formulae. Okay, drag force, lift force, right? And this is how I basically did the calculation. This is the bottom view. This is the front view, right? What area will be used to basically calculate what, if drag force is being calculated, so what area you should take. In many studies, they will take the surface area. But in my study, what I did is I basically took the frontal area to calculate the drag force and the bottom area to calculate the lift force. Okay. And this is how I did the calculation, L by H. So that will be the surface area, and bottom view, L by X. Right? But usually people take surface, again, depending upon with what you are, validating. Okay. These are the formula for, I've just extended that, right? Since we are running the 2D and how to get the dimensions and all. So guys, this is the kind of thing which industry is expecting from you, that you are doing something, documenting it, providing explanations, so that can be used as the intellectual property for the companies, right? Now, when I was basically, talking about, Y plus and all, right? So see guys, basically, see what is Y plus. See, I will not dive deep, okay, because that's again a heavy concept, but still, since I have talked about it, see, let's say this is a body. Okay, let's say this is a car, for example, and it is basically placed in a wind tunnel. Sorry, this is a wind tunnel. First thing, before I talk about Y plus, this is called as inflow length. From inlet, till the body, this is inflow length, which should be 5 times L. What is L? The length of the body. Your outflow length should be basically 15 times L, ideally. And this height should be 5 times L. Okay, this is general industry practice, but when I ran, I didn't take 15 times L. Otherwise, till now also my, that simulation would be running. Okay, so obviously we have to compromise on that because of the resources and all. But the thing is, when you're going into the industry and all, they will be having supercomputers and all. You will not face these things. But the point is not to basically stop yourself from learning because I don't have the resources. No, you are here as a student to learn the methodology. You should know how to set up this case, what should be there. Okay, what is outflow length, what is inflow length, right? What is free stream velocity, right? What is basically separation zone, what is recirculation zone, what is stagnation zone, what is drag force, what is down force, why it is so important, right? Those things if you know. Now let's say if you are not able to run on a finer mesh, okay, or you are basically not able to keep this as a 15L, so what? You basically kept 5L and you kept this as 3L and you kept this as a 3L. Okay, fine. You can't go with meshing. You can't go for, let's say, 3000 cell count. Okay, you went with let's say 1000 cell count. What's wrong with it? It's okay. The point is you are not doing the validation study here. You are learning, and with the 1000 cell count and with this parameter also, you are going to get the reasonable physics. You will be able to capture the physics very well. The thing is, when we tell that to refine and keep these things, because when you are going to validate the results. Okay, so now tell me, anyone, that let's say if I'm not keeping this outlet far away from the body, let's say instead of that I'm keeping it very close, let's say here I'm keeping, okay, very close to the body, what will happen? What will be the drawback?
Sir, backward flow will be there, sir.
So what? Backward flow is there, so?
Sir, so velocity will decrease, means the drag force will increase, sir, to the car.
No.
Means we will get wrong result.
But yeah, you are right. We will get wrong results. But why? The reason you are telling is not right. I mean, partially right. There is a reversal flow, but you're close to it. But try to give, come to the, you're marching towards it. Can you basically think of it some more on this? Anyone can participate here. So the thing is, I'm rushing because we are running out of time. But the thing is, what will happen is, let's say, see, outlet, correct? So outlet means what? Your flow is coming out, correct? This way. Agree?
Yes, sir.
Yes, sir.
Your flow should come out like this. But let's say if my outlet boundary is here, see, I have provided this as an outlet boundary. Means Converge has assumed that this is outlet and flow will come like this, because that is my boundary condition, correct? I have told my solver that this is outlet. That's it. Outlet means flow should come out of the domain and it should not come into the domain. And inlet means flow should come into the domain and not go outside the domain. Now, let's say if I'm not keeping this far away, the outlet boundary, the thing is, the point which one of you mentioned about reversal flow, what will happen is there is a reversal flow like this. And if this reversal flow is not died down, what will happen is it will happen like this. So from the outlet, there is a reversal, which is contradicting your boundary condition. From outlet, now the flow has started to enter into the domain like this because of reversal flow, correct? But your boundary, your boundary condition is saying, that it should be like this. Now your simulation will give you very wrong results, very, very vague results, or it might crash also. Is this point clear?
Yes, sir.
Right? Outlet means you only are telling that this is outlet. And what is the meaning of outlet? That your flow should come out of the volumetric domain. And because of, if the reversal flow is not died down, it will basically there will be a reversal flow from the outlet, meaning flow will start coming into the domain again due to this reversal flow. and that will basically contradict your statement which you made in your boundary condition. Okay, so that's why we are keeping this boundary outlet a bit farther away from the body, so that this recirculation zone is died down, and eventually when it is died down, it will automatically come out as a u infinity. Make sense? So guys, these are the things you have to focus on, rather than which software I should go with, ANSYS or Converge, or I should go with SCFlow, or I should go with whatnot. No, that is not the point. Whichever this software thing, the language thing is just a matter of 2 weeks. Or if you're saying I'm very slow, 1 month, that's it. What more it will take? But the major thing in the interview, they will absolutely test that. If you're saying that I did ANSYS, so they will give you some problem to basically set up and show the results, so you should be able to do. But the thing is, if you are not able to explain the results, that hey, why there is a recirculation zone. Okay, great. Here only tell me why here recirculation zone is created. Can anyone tell me why?
Sir, because of flow separation.
Due to the lower pressure.
Okay, why lower pressure? What made it
So,
create a lower?
if I may. So if I may.
Sorry.
If I may speak, yeah. So what happens is that, sir, when the fluids cross over the object, they hit towards the object. I mean, they hit to the area that's present there, and they get driven back towards the object. If I'm not wrong.
Sir, it is a velocity difference only, sir.
Sir, it is
They
velocity
get
difference.
bounced by the.
Sir, drag resistance on the fluid of air.
Guys, still I'm not satisfied. If you're giving this kind of answer, interviewer will not accept this. Okay.
Sir, we keep the pressure equal to 0 at the outlet condition. So like means like pressure equal to 1. So there is a pressure difference between the inlet and outlet.
But the thing is,
So,
pressure. This outlet is here. Okay. Let me just rub a couple
Yes,
of
sir.
things here. 1 second, so that it is confusion is not happening. 1 second. Okay, this thing is not there now. This is here. Okay.
Sir, because of flow separation, it will occur, sir, wake formation.
But why flows? Okay, flow separation is happening. Okay.
Sir, because of shear stress, sir, because shear stress increases as the length increases. So because of there will be a flow separation, and the flow is separate and form the wake.
So now if I tell you, if you don't go that much complicated, it is very simple. How? Keep it very simple, guys. How you can keep it very simple? If you know the things, from basics, like whatever you are saying, trust me, I didn't understood those things. Pakka. You might be right, okay, but I didn't understood. Why I didn't understood is because you basically, what students are trying to do is they will try to make the things more complicated, and they will try to put it in front of the recruiter in such a way that they know a lot of things, but you are putting yourself in trouble there. Keep it very simple, the interview. If you use the layman language also, but you are explaining it correctly, no one will reduce your marks. Okay, those technical language and all will develop over the period of time. But the thing is, the why it is basically creating here, right? First thing is, here the flow is coming, and suddenly there is a separation, right? Flow is attached, and suddenly it is going like this. So here there is a fluid coming like this with u infinity. Obviously it will be affecting the resistance will be there and all. Let's say this is happening. Now what is happening is it is coming with some velocity, correct? So now what is happening is, here there is a sudden separation, and here already there are air molecules, correct? Till the time this air came, okay, these were in a static position. Okay. These were in static position, means there was a static pressure. Now when this velocity came with some force, this basically disturbed the static pressure of this molecules. So what happened is, static pressure decreased and dynamic pressure increased. correct? So static pressure is decreasing here and dynamic pressure is increasing. What will happen here is, guys, that here this molecule, right, this molecule will basically move this side. This molecule will move this side. This molecule will move this side. And here there will be a void, big void created. And here, since there is a void means what? It created a vacuum. Vacuum is basically and here the fluid is hitting the wall. So here what is this? Here it is a high pressure because this is a stagnation zone, correct?
Yes, sir.
This is a stagnation zone, high pressure zone. Here volume, here because of this thing, vacuum created, a void created, and this is low pressure region now. Now, because of, so now see, imagine, okay, here, let's say, let me rub here. Oh shit, okay. My bad. Quickly. So here is a high pressure zone. Here created a void. So I'll create it with blue. Let's say here is a void. Okay, I'm exaggerating. This is a low pressure region. Now what will happen is, see, here is a void, but here there is a air. So here is a low pressure. Now imagine, okay, now here is the low pressure, but there are particles here. There are particles, right, which are at the which are still at the static, pressure only. So here basically pressure is high compared to pressure here, right? Because here already a vacuum is created. So now what will happen is, basically from high pressure to low pressure, this molecule will get sucked in, and this will give rise to recirculation zone. Am I clear with this concept? Guys, am I clear with this concept?
Yes, sir. Yes, sir.
So the same thing is happening, guys, with the backward facing step problem also. Let's say I am having a this is a backward facing step, okay? This will, you can see this in many applications and all, but let's say this is the inlet, this is the outlet, and here basically flow is coming, okay, flow is coming, and here sudden there is a separation. So again here there will be a recirculation zone because of the same reason which we discussed. Here the velocity with which it is coming, it will disturb the static pressure. Static pressure will reduce. It will make the molecules move to the left hand side. In this case, there will be a void created here, which is a low pressure region, and there is surrounding it, there is a high pressure zone compared to this zone. So from high pressure to low pressure, the molecule will get sucked in, and this will give rise to a recirculation zone. Okay, that is why recirculation is created here, or you take turbo machinery application, or you take Ahmed body application, whatever you take. Okay, so these are the things happening, guys, right? So now let's any questions here, like question in the sense, any doubt here?
So can you please elaborate a bit more on how static pressure is decreasing and dynamic pressure is increasing?
Sure. So there is already a challenge, channel fan backward facing step, where you are going to do that. But the thing is, total pressure, there is a term called total pressure equals to static pressure plus dynamic pressure. Okay. Oops. Okay. So static pressure and dynamic pressure, basically if there is a box and there is no movement, okay, air molecule, it is not moving at all, okay, this box is not moving, and there is no external force which is making these molecules rotate or whatever, then the pressure which this molecule exert on this box surface, normal to this box surface, this is called, the pressure which box is experiencing because of molecule is called static pressure. But when there is some fan or something kept on, and basically, what we say, it will disturb the molecules, then static pressure will decrease and dynamic pressure will increase. So the thing is, if I need to rub this, so the thing is, this is a wind tunnel and this is the inlet, and from here flow is allowed. This is your outlet. From here flow is coming out. This is your body. Okay, and here the flow will come and hit this surface, and here there will be a very large pressure, and that is why this point is called as a stagnation point or stagnation zone, where there will be a high pressure. Now the thing is, flow is basically coming like this, it is attached to the boundary, and suddenly boundary basically, there is an abrupt change, and flow is basically, separating from the wall. Now since flow is separating from the wall, so obviously there is a layers of fluid coming, right? So basically this is what U infinity, here it will be U infinity, here there will be a gradient. Okay, that we'll be discussing shortly, but there will be a gradient. So basically this U infinity, or whatever, with whatever velocity less than U infinity, to be keep it general. Okay, whatever the U which is less than U infinity in the boundary layer, with some velocity it is coming, right? But before this air came, okay, whatever the molecules were here, they were not disturbed, correct? Agree, guys?
Yes,
Yes,
sir.
sir.
Yes, sir. Yes, sir.
They were not disturbed, so they were exerting static pressure and shanti se baithe the. Okay, and basically when this flow of air came in, or let's say you on the jet, okay, of air, so high velocity air is coming, it is basically disturbing these molecules. Now the molecule which was here, because the direction of air is this way, so it will drag this molecule here, it will drag this molecule here, it will drag this molecule here. So till the time this is getting filled with another molecules, for fraction of second there is a void, right? There is a void getting created because molecule got shifted from its original place to some other place, correct? So here there is a void created, right? Now since here is a void, so void means was nothing is there. So if nothing is there, what will exert pressure there? Nothing. So it is a low pressure, and surrounding this void, so it is like, there is a air balloon, okay, and surrounding there is a very, high pressure. So it will burst the balloon, right? If here pressure is more, here pressure is less, so basically PS is more than P, then this will burst P, correct? This will burst the balloon. Similarly, this is a void. Surrounding this void, there is a high pressure molecules, or high pressure zone is there. So from and we know in fluid the things will move from high pressure to low pressure. So from high pressure zone, the molecules will get sucked into this low pressure zone, and this will basically give rise to recirculation zone. Is it clear now?
Yes, sir.
Great. So now the another concept of Y plus which we are going to discuss is this. Okay, why Y plus is very important. See, again I will create a wind tunnel, and again basically I will create a small body. So now you are going to see this is inlet. You don't need a very fine mesh throughout the wind tunnel. Understand this. You don't want very small box throughout the wind tunnel, because anyways we are interested in what? We are interested in the flow physics around the body, correct? We want to basically know how much is the drag force experienced by the body, what is the down force experienced by the body, right? This is the thing we are interested in, correct? And what is the recirculation zone? So let's say this is our zone we want to focus on. Okay, now this is the wind tunnel. So do you think that if you are not interested in this rest of the part, we need the very refined mesh there? No, right? It is unnecessarily you are creating a lot of mesh and wasting your time, computational time. So what we do in while setting up the cases, there is a term called base grid. We'll put that base grid will be common to the entire region, volumetric region. Okay, now my concern is I want my mesh to get refined in this region only, not in the entire thing. So I'll basically select this. I'll make use of fixed embedding, volume embedding. So there are a lot of things where I can basically select that. Okay, this is a sphere, so I can basically, okay, let me use rubber. Okay, so let's say there is an option called volume embedding, so which Converge provides. So what it will tell me, okay, create a box around which you want the your mesh to be refined. So what I'll do, I will create the box of this much length. Okay, I want my mesh to get refined in this region. Then I will basically say fixed embedding, and I'll select the boundary like we selected there, that Ahmed body, whatever the boundary name is, this. Around this, I want fixed embedding. Great. So basically here, it will basically, do like this. It will refine this. It will refine this. It will refine this. Right? It will refine this. Like this, it will refine. Okay. So when you refine, so base grade divided by 2 power n. This is what your refined mesh formula is, which software uses. So my base grade is, let's say 5 mm. I want near my, in this box, I want to, let's say 6 mm. I want in this box 3 mm. And near the body, I want 2 mm. So what I will do is, I'll basically 6, and for this volume embedding, I will keep n as 1. So 6 by 2, which is 3. So in this box, there will be a mesh element of 3 mm. Okay, it will distribute accordingly. Okay, and now I want near the body, I want it to be 2 mm. So now what should I do? Right? So now here n will take the integer value. So if I am having 6 mm divided by, if I keep n as 2, so it will be 6 by 4. Right? If I basically keep 1, then it will be 3 mm. So I will basically keep this as 2, and I'll divide this, 4 ones are 4 and all, and that will be my mesh here. So why I did this? See, ultimately, this is U infinity. I want to basically understand the flow physics around my aerodynamic body. That's it. I'm not interested in wind tunnel and all. Okay. Now the thing is, if I'm interested here, so the thing is, do you think that when the flow is happening there, it is going to basically create a boundary layer like this? Because there is a surface, it's like a flow or a plate only, right? Flow or a flat plate. So there it is going to basically, having a boundary layer where there will be a gradient. Okay. Velocity gradient, pressure gradient, and all the gradients will be there in this boundary layer only. Outside this boundary layer, everything is U infinity. Agree?
Yes, sir.
So I want to, basically, if I want to capture, I have to capture this boundary layer, correct? Now to capture this boundary layer, now boundary layer is having multiple, sections. So it is having log low region, it is having turbulent region, it is having laminar region. So to capture the laminar region, your Y plus should be 1, which is not possible to do in your normal laptops and all. Okay, it needs a supercomputers and all. So for log low and turbulent region, if you want, you can basically keep your y plus between 30 and 100. And even, I have actually basically kept y plus to be 300 and all. I am getting the reasonable results. See, I can't afford this, so I will not go with it. That's fine. I'm interested in learning. Learn how y plus is calculated and what is y plus first of all. So let's say this is a body. Okay. So and this is, let's say, the first cell. So the distance between the center of the first cell from the surface of the body is called as delta S. This is delta S, and that is what representing that is what will represent your y plus value. If your y plus is very low, it will end up having a lot of cells, because this size of delta S will keep on decreasing. If your y plus is 30, then your box, the first cell height will be this much. But if your y plus is, let's say, 10, your box size might be this much. And if your y plus is 1, it will be very thin, the first cell. So y plus is basically representing the distance of the center of the cell from the surface of the body. This. And in technical terms, it is called as delta S, which will basically represent that y plus, it represents y plus. So this is very important, and based on this, your cell count will be determined, how many cell count will be there, and basically based on your turbulence model also, whether you're, which kind of turbulence model you're using. Are you using RK, RNGK epsilon, or you're using basically, different, turbulence model? That will basically decide that what should be your y plus. And there is an online available y plus calculator where you have to provide the U infinity, Reynolds number value and everything, and it will give you y plus value. Or if you want to do the reverse calculation, provide y plus and it will give you other quantity which you want to find. Right? So this is important thing, guys. And this is what is you're going to learn in the aerodynamics course. Initially, there will be challenges like flow through channel, flow through backward facing steps, so that you understand how to basically and analyze the results and explain the results and understand and become comfortable with the graphical user interface of Convert CFD. But in the aerodynamics, there are 3 major projects: floor and airfoil, Ahmed body, and FSA racing car. For Ahmed body, we are also doing experimental validation also. We have experimental data with us, right? So let me show you that. And here, basically, I applied my knowledge of coding also to basically validate my results. I will show you how. So this is, again, I have my habit of, documenting everything. So this is Ahmed body results, right? So I have basically, this is a stagnation zone, this is a separation zone, right? This is a velocity, magnitude and all, right? Then I'm checking, at different angles how the things are there, right? See, this is the pressure contour. So I'm mentioning this is a high pressure zone, right? Here, it is a low pressure zone, low velocity zone, correct? Then this is basically y plus all over the Ahmed body, correct? So if you see, this y plus is basically a 130, okay? You can see at many places it is 130, right? So I can't go with 1, right? So see, low y plus region, refined mesh. I told you, right? If you go very low on y plus, your cell count will increase, and your cell count is increasing means what? You are having very small cells, means you are having a refined mesh. And I have basically selected this much region only. Why I have not selected entire region? Because I'm interested to know the physics here only. I'm not interested to know the physics everywhere else. So that's why I have kept everywhere else the coarse and mesh. Only this is my refined mesh. If I show you the mesh thing, right? See, this is what I was talking about, volume meshing and all, right? See, everywhere there is a coarse and mesh, and I have created a box with the help of Converge. It is very straightforward. You will give the dimensions. There is an option to give the dimensions. You'll create a box, and then you will define that what level of refinement you want in this region only alone, right? And to closely look, see, out of this refined mesh, everywhere else is a coarse and mesh, correct? This is called as box embedding. So only this much part of the wind tunnel will be refined. And now, but near the body also, I need, much more refinement, because there is where my boundary layer is forming and all the, so the thing is, if I'm refining this much region also with the box embedding, my boundary layer can be ending here only. Okay, here again it might be u infinity, but who knows? So I want to refine near my Ahmed body also, right? So this is what I did inside the box near the Ahmed body. I refined this. And this is called as boundary embedding, fixed embedding. Inside fixed embedding, there is a boundary embedding. I basically refined there by another level. So this is, let's say 3 mm, then this is 1 mm. And I have created that such like 3-4 layers, 5-6 layers, correct? I think 10 layers are there. If I don't keep 10 layers, what will happen? Can anyone tell me, if I don't keep 10 layers, will I be able to capture the physics?
No, sir. No, sir.
Right? We basically discussed that we need at least 6 to 10 cells to basically capture that parabola, right? Similarly, because in the boundary layer only, there is a gradient. So you need to make sure that you are basically not refining the mesh much. You are going, instead of keeping y plus 30, keep y plus 100. But make sure that number of layers are more, so that you will be able to capture the physics. Right? So here I have kept the number of layers as 10, and I have kept the scale as 3. Right?
Sir.
Yeah.
Sir, I want to ask that means we have to make boxes, means like we have create the enclosure, 2 enclosures, like first for that near the car, and then one big
yes.
box.
That like, one big one is the wind tunnel, entire wind tunnel.
Yes, sir. So which one will be better, sir? We have to create this in ANSYS like software. We have to create sphere influence like thing. Is better, or we have to create the box and then refine the mesh? It's better, sir.
Again, depends. Okay, I'm not a big fan of ANSYS. Okay, but I have done my work on Converge a lot. In Converge, it provides, in Converge, it basically provides me sphere also, box also. I'll show you. Fixed embedding. Oh, I closed that. No. Here it is, right? Great. So see, I have provided base grid as 0.028, 0.189, and 0.028. Why I did like this? So that I showed you, right, how to stretch the mesh. Along the Y direction, I'm not interested in knowing the physics, but along X and Z, I'm interested. That's why I kept it like this, and it created the mesh, overall mesh like this. Now I want to refine it. So here I'll go to fixed embedding, right? I went to fixed embedding. Here, the first embedding, if I see, it is permanent Ahmed body. Near the Ahmed body, it is giving the scale. I am given the scale of 3. And while setting up, I started with 2. But I didn't get the good results. I did 5. Still, I didn't get the results, 10. Then I got the results. I'll show you how I got the result that. But here, see, entity type box, it is giving me option of boundary, sphere, cylinder, box, region, right? Nozzle, injector, if it is there, right? So here you can choose anything. But here, which is better means, for me, if you tell me, it is better to keep a rectangular box, because here the wind tunnel and everything is in that shape. If something is in the spherical or round, curvy shape, I will go with spheres, because it will basically choose, it will cover that much area in a very effective way. If I choose here, spherical, then also it might serve the purpose, but it doesn't make sense to go with sphere here. So again, it depends upon application to application. Making sense?
Okay, sir. Yes, understood.
Great. Then, so if you see layers 10 now, okay. Now here is what the validation study happens. So I will show you first the validation data. Okay. So this is the experimental data we have. Okay. We got actually from the industry and all, we got this data, and this is how, I basically, the data looks like this. Okay. For different simulation and experimental data and all. So they have basically ran experimentally in open form. Okay. They have done a lot of studies. Now we want the experimental data only, because we want to compare the experimental data with other data. So what they have done is, So this is the body, okay, Ahmed body, and at different X location, or in this case, yeah, different X location, they want to they plotted the probes in vertical direction, okay. So at different X locations, they want to see how X component of velocity is changing along Z axis. Vertical is Z this time. I hope you are not confused now. So vertical is Y. So at, let's say, at Z equals to 700, at Z equals to 600, at Z equals to 500, at Z equals to 400, I want to see what is the X component of velocity. That is what I'm checking, and that to different X locations. Clear?
Yes, sir. Yes, sir.
Yes.
Clear, right? So the thing is, this is what I want, and this is what is in the experimental data also. See, U experiment, U meters per second is the X component of velocity, and at which X location and at which Z location, what is the value of U, right? So let's say at X equals to minus 13, there are multiple Z values because it's a vertical line. So multiple Z values, what will be my U? So this is my U at multiple Y values or Z values at X equals to 30, minus 30. So now this is the experimental data I have. What I did is I just filtered it. I created a new Excel sheet for myself, and I put all the experimental data here, or at various X location. X equals to minus 13, then X equals to minus 263, then X equals to 37, then at X equals to 87, right? Like this, I basically created a probes also in the post-processing tool called ParaView. Okay, how I created those, that is also covered in the our video in our lectures. But this is what I did. I basically imported my post-processed results in the ParaView, and then basically I created the probe like this at X equals to minus 13. This is the velocity profile at X equals to minus 263. This is how I got, right? And then what I did is I basically make use of Excel, where I have dumped the experimental data here, correct? Here I have experimental data. What I did is I basically merged two plots, and this is the error bar, so that if the error is within 5% or 10%, it is good, right? But obviously it is most of the time it is within 5%, 10% or 5%. But again, I have not ran on a very finer mesh, but that's not the point, right? So here basically I plotted. Then next thing, basically at X equals to minus 113, I plotted another probe. And here I basically I ran the simulation, correct? So I have all the data. I have the pressure data. I have the XYZ component of velocity at XYZ. I have all the three components of velocity at everywhere wherever there is a mesh, right? So basically this is the velocity profile at X equals to minus 113, which is this location. And I am basically plotting UX, X component of velocity, not Y and Z component. And this is how the profile looks like. And basically the black one is the experimental data. You can see that how closely it is matching, right? Right. So this is what is the validation study you are doing against the experimental data. Again, I basically plotted again minus 63, validated the results, basically minus 13, okay, validated the results, minus 37, validated the results, this validated the results, this validated the results, correct? So at different probe locations, so these are my all probes. I basically created all the probes at different location through ParaView, which is very straightforward and explained in the videos. You can basically create these probes, plot X component of velocity, okay, and then basically use that data and plot the graphs in Excel and get this kind of graphs. Simple. And then I did the same study in OpenFOAM also, right? So OpenFOAM is a bit more, it is following the trend, but it is much more deviated as compared to converged results, right? But if we do OpenFOAM much more nicely, it will basically give you good results there also with OpenFOAM, right? So if you see, OpenFOAM results are much more deviated, but following the trend at least. This is what you have to focus on. Even if your basically your data is, somewhere here like this, but it is at least following the trend, that's enough, because you don't have the sources. But what we did do is, we basically ask students to run the case on course and mesh, show us the results. If results are reasonable, we basically provide them the outputs which we ran on the finer mesh, and they can use that to basically write their reports and showcase such kind of results, right? Then basically here in the experimental data, if you see, it is basically the normalized plot, right? They have normalized the plot, and basically they have plotted with for different simulations and experimental data, open form results and whatnot. So here we will also do the same thing. Okay, what we basically did is, we also created a normalized plot. Can you see this? So if I basically this thing, right? So these are the normalized plot. If you see, red one is converge, blue one is open form, and black one is experimental data. How I did this? Now I made use of coding, which we yesterday did, right? We did coding, and I told you for the application engineer also, it will be very useful if they know a little bit of coding. I am not the master blaster in coding, okay? I just know the little bit of coding, because I am a kind of application engineer kind of a guy, okay? But I realized the importance and the strength of coding if you know it. And when I the first course I learned was MATLAB, okay, like 3-4 years back. But the thing is, these are the courses when I learned, and when it came to the implementation, I prefer to do this thing by coding and not in Excel. You can do the same thing in Excel also, but I felt much more comfortable writing a script rather than going with Excel. Why? Because it is making my life very easy. How? Just take a look. Okay, I made use of Octave. Okay, Octave is similar to MATLAB, but Octave is an open source which looks similar to MATLAB. Okay, this is the editor window. This is the command window, right? Here it is a workspace. Here it's the current file browser folder, everything. What I did is I started with clear all clausal CLC as usual. Then I basically at x equals to minus 13 here, to make this comment out, I have to make use of pound, okay, and not the percentage. In MATLAB window, I have to make use of percentage and not pound. So if I do percentage here, then it will become a comment, right? But in Octave, I have to basically make use of pound. So that's again a syntax, right? So basically this is what I ran the code. Okay, sorry, I wrote the code. Now what I did here, simple. What I want to plot, this is the simulation data which I already have, because I ran the simulation, right? So I basically copy pasted the data and put it in the square bracket. I created an array. Okay, we created an array and all this thing yesterday in the square bracket. I did the same thing. I opened the square bracket, put all the data, close the bracket. Now then, this is to normalize the data, and I will not go here into the math, but to normalize the data, you have to provide the amplification factor and all these things, right? And now simulation results for the velocity at 13th location. This is another variable name for my simplicity, that this is the velocity of u at x equals to 13. It can be my name also, but for me to understand this code I wrote, you will not believe I wrote this code at least 2 years back, or at least 1.5 years back. Okay, but this after 1 year I'm opening this code again, and I'm able to understand each and everything. Why? Because here I have written all the comments. I have given the reasonable variable names so that I can understand. Now what I'm doing, I'm indexing. So what I want from simulation 13, what is simulation 13? This is simulation 13. This is simulation 13, which is the variable name. Now from here, I want to extract some data. What data I want to extract? I am trying to basically extract all the rows of 5th column, right? So this is 1, 2, 3, 4, and 5, 5, right? So I'm trying to basically extract the 5th column of, and I want all the rows. of it, because I know that here, see, Octave will not understand that out of this 1, 2, 3, 4, 5 columns, which column contains velocity value, right? So I have to specify that, okay, I want all the values from the 5th column. So it will be, I have to refine it. And there is a way, all rows of 5th column. Then I want Y location. So from simulation 13, all rows of 2nd column, because I know at the 2nd location, there are all the Y locations, right? Then I basically make use of the formula, right? All the values I took and I divided it by the maximum value of the velocity at that location, and then multiplied it by the amplification factor. See, this is a simple math, okay? If you're getting confused with that, forget it, not to worry. The whole idea is I'm trying to explain you the importance and the strength of coding. And you will see how many values I have to type. No, you just have to copy paste. You just have to type experimental 13 equals to, open the bracket, copy paste all the values, close the bracket. That's it. And write these 3 lines and then copy paste for all. How much time it will take, right? This code is basically, you will say, this code is 1354 long. Oh, but I have just copy pasted the data, created an array, I understood the syntax, how it works. I basically, copy pasted those data which I got from the simulation into the coding. I created an arrays, and then I basically plotted, and I basically feed in the formulas which will help me give the normalization values. And this is all figures I plotted, and then finally I gave the labels. Okay, everything I gave, hold on, hold off, whatever we learned yesterday, everything is used here, right? Simple things. You just have to practice, and depending upon the application, you will automatically use it. You don't have to mug up, okay, hold on, where I have to use, where I don't have to use, where I have to use plot. No, wherever it is needed, automatically, chamkega. I mean, automatically the, your bulb will, get lighted, because you already have practiced a lot. And when your application is demanding that, you will write. Now code is ready. Now just run the code. That's it. All the data came here. I just ran the code. That's it. Hope you are able to see the code, right? This result.
Yes, sir. Yes, sir.
How much? When I hit the run, in fraction of seconds, it did all the calculations, right? Correct?
Yes, sir.
This is the importance. Now let's say if something is changed, okay, let's say I ran another simulation for the same thing. Now the boundary conditions and everything is changed. What I have to do, I'll just copy this data, I'll delete it, and I will replace with the new data, and I'll just run it. 5 minutes job, I'll run it again, I'll get immediately another plot for the different boundary conditions. That's it. Now, if you are not writing a code, you are basically doing the manual calculation and all, how much time it will take? You have to, let's say you have to run such cases like 100 times. So you will keep on doing 100 times those calculations? No. Just write once the code, spend 1 hour, 2 hours, whatever. That's it. Done. This is the importance of coding. Right? So this is what I did. I made use of Octave. Okay. I can do the same thing in MATLAB also. I did it here also. Correct? So basically MATLAB and Octave are pretty much same, but Octave is open source. MATLAB is a paid version. Okay. And yeah.
Sir, what about Skylab, sir? Skylab is also okay, sir, for this.
Sorry?
Skylab software, sir.
Yeah. See, it again, depends. Okay. When I was using Python, so I was using Sublime. Okay, so I'll show you. Okay, I was using Sublime to write my code. So Python, again, this is a coding language. This is the here you will write your codes the way you wrote in MATLAB. The same code I will write it here. Just the syntax will change. I think yesterday we did auto cycle, right? I will check if my auto cycle, OD we did, right? So I'll check if OD is there. Unfortunately, I don't have a code right now. But 1 second. I can do one thing. Super. All right. We were looking for ODEs. So ODE I have a not simple pendulum ODE. So we are done almost, but I just want to show you so that you can understand that it's not a big deal. Anyways, so I can show you for auto cycle. Now see, this is the code I wrote in Python. I created a function also, I created everything. But there is some different style here. Now, what thing will, make us, feel scary? These things, colorful things, import, and this, it is coming in italic and different colors. Then this, what is this? This I made it just a comment. I commented it. That's it. All different colors. It is good for our readability. Right? I just make it as a comment, and basically I'm writing this code. So why I imported this math library? Why I imported this matplot? Because that is what it will require if you want to plot. So like in MATLAB, we were using plot X, Y, or whatever. Here it will ask us to import the library first so that it can basically use that library to plot whatever you want to plot. In MATLAB, we were doing dot operator, right? Or we were doing subtraction, multiplication, whatever. So to do those kind of operations in Python, it is telling that you have to import math library. Simple. There are a lot of libraries like SciPy, Math, Matplotlib, whatnot. To ODE, there is a ODF, there are ODE solvers in particular library, so which you have to import. Then I am basically defining my function here. This is my function. This is how my, that equations are basically what we say, governing equations, right? For isentropic, compression, expansion, and all, right? And this is basically, here I'm writing the for loop. Didn't we do the same thing in our MATLAB? The same logic, right? The same thing we did here. That's it. So what's a big deal? This code is very long because I have basically mentioned a lot of comments so that when I'm reading it after 2-3 years, I can understand what I have done here. And finally, I'm basically plotting. So what is the syntax? plt.plot. You have to write like this. You can't write directly plot. And if you want to show, you have to write plot plt.show. You can't use semicolon. Simple. This is what syntax. No logic. Logic was that you learned while doing the MATLAB. The same logic you will be using here because the formulas are not changing. Logic will not change. Just the language is changing. All right. So I think it's already 7:05. We are done with this, right? But okay, I want to basically show you one thing. So yeah, this is the original geometry of hot oil, cold oil. Okay, these are the number of cabinets we have. Okay, and again, these are the things I have explained. Okay, why there is a need of a porous media, temperature increases, density decreases. So these are the things you should also practice doing, so that when you are preparing for interview and all, it is very easy for you to basically go through these things and get it revised. So this is the reason I'm showing this PPTs. Otherwise, there is no reason to show you all these things, all my work, right? The reason I'm showing it to you is so that you can also follow and prepare your Word docs, PPTs, everything. This is shell and tube heat, right? This is shell and tube heat exchanger. Basically, this is a part of HVAC course. So the shell and tube heat exchanger geometry I showed you, right? So this is what you have to explain, that why baffles are needed, and you are able to capture the physics also. So what kind of physics is needed, right? Why it is very important to choose the material of the shell and tube heat exchanger very wisely, right? All these things you should explain when you are writing the reports. You are doing counterflow, you're doing parallel flow, yeah, do it. Explain those things. What is LMTD, right? If you don't know these things, it's a good time to understand these things and apply it here, right? So these are the things you have to do. Anyways, we are over time. I have to stop. I don't want to stop. I want to cover. I have planned for a couple of more things to show you. But before we wrap up, this is the port fuel injected engine, IC engine project. I'll play it. So this is how, okay. I think someone asked me about spray modeling, correct?
Yes,
Is that
sir.
person available? Yeah.
Yes,
so
sir.
spray
Yes.
modeling. So can you see here the spray? I'm basically injecting fuel in the form of spray. This is how the injectors will spray the fuel into the port fuel injected engine. So this is basically where the importance of spray will come. Fuel came, intake stroke started, mixed with air, came into the cylinder.
Okay. Sir.
These are two intake valves, two exhaust valves, cylinder, liner, exhaust port, intake port, injectors, fuel getting sprayed, mixing. That's it.
Sir, how can we specifically say this amount of molecules are coming inside?
Exactly. So for that, basically, that's actually a 2 weeks project. Okay, the major project in IC engine. So that is what you are going to basically, usually people run the dry case first. They don't use fuel first. They will use air, and they will basically run for 20-30 cycles, and they will see that how much air is getting trapped first in the cylinder region. Okay, and to burst, basically to if that much air is there, you can determine that how much fuel you can basically allow, because otherwise it will be a lean mixture or the rich mixture, correct?
Yes, sir.
So that should not happen. If it is a lean mixture, then problem will come during the exhaust. If it's a rich mixture, again the problem will come.
Okay.
Right? Yes. So NOx will produce, then carbon monoxide and all these things will produce. Correct. So great, guys. It was a nice having a word with you all guys on this. But last thing which I would just show you.
Sir, if you could suggest some manuals or notes that we can, if you can suggest some manuals or some notes like we can learn the basics through it for MATLAB and Convert Studio.
So see, basically, for MATLAB, it's basically you have to practice. Okay.
Yes.
If you are basically, I don't know whether you have taken these courses or not, but if you have taken, then basically there will be a lot of practice challenges you will be getting. First finish those things, and then we also have a lot of projects which we have worked on, which we can provide you guys, okay, for you to practice, right, the application of what you did. So that is how you will become good at it. And then when you're taking Converge things and all as a coursework for you, these are the things you will be doing with, and whenever you are stuck in, you will ask your support engineer, and those doubts you will be resolving. But you will basically get the licensed version of software for 3 months. You will complete the course, you will watch the videos, you will set up entire case setup all by your own. You will run the case setup, then you will post process the results, and you will be coming up with this kind of animations and all. Right, this is the combustion animation. Okay. So this is a combustion emission. There is a spark plug, there is a spark, combustion. Now spark will ignite, then flame propagation. Ignited, flame propagation. Now this looks good, but after this, what to do? It has ran the simulation. Lot of data is basically dumped somewhere. So now you have to basically make use of that data to get very important and useful plots like in cylinder pressure, temperature, heat release rate, okay, integrated heat release, what is the volumetric efficiency, what is combustion efficiency, right? All these things you have to calculate and basically put those things in the report, right?